So this is just some examples of some of the energy bar chart problems we've been working on. These are different ones than you have on your assignment. And I'll go through, I think I have 5 on here, and talk through each one of these. So the question is, at this point, if you want to pause it and then try to solve it, you can, and then I'll work through it here. So when a small piece of sodium metal is dropped into a beaker of water, hydrogen gas, and a solution of sodium hydroxide are products. The solution becomes warm. So what we have here is we have sodium and water reacting together. We have one product that is NaOH and one product that is H2. And as a result of this, it becomes warm, so we have energy as a product over here on the right side. Balancing this equation, we need a 2 here, a 2 here, 2 here. So from this point now we can start to put into our bar charts where things go. Since this is the solution becomes warm, what that means is this is an exothermic reaction. And so we're going to have energy leaving the system at some point. Where that energy comes from needs to be in the thermal state. Where the energy originates from is in the chemical state. So to start with here, the first part is these are the reactants. And we have probably 4 bars of chemical energy here. And we have, since it's basically at room temperature, 2 bars of thermal energy. So the first thing that happens is we have some chemical energy that changes over to thermal. So in terms of our energy flow, nothing is entering or exiting the system yet. But now we have 2 bars that have moved over to thermal. We still have our original 2 bars of thermal, and now we're just left with 2 bars of chemical energy. So if we change chemical into thermal energy, what happens is the temperature, spelling temperature wrong here, temp goes up. So when the temperature goes up, the heat then begins to leave the system. So I've drawn 2 bars here that are leaving the system. Those are coming from, again, the thermal energy section. So what I have left at thermal energy is just 2 bars. Chemical energy here is still 2 bars. So kind of coming up here to the top where there's some blanks here, well, these are the products of the reaction. So as the reaction proceeds this direction, we get products. Now those products produce energy which will eventually leave the system. And so we call this products also here, but this is later on. So when something is heated up, when there's thermal energy to it, eventually that's going to cool down. It's going to lose that thermal energy. Second one here is, and pause it now if you want to try this on your own, heating potassium chlorate powder produces potassium chloride and oxygen gas. So this part is key here, heating something, so that means that this is endothermic, which means we're going to be adding energy to the system. So let's start by writing the reaction out here on top. You have potassium chlorate, which is KClO3. It's an ionic compound. And then you have products KCl plus O2. And to balance this, you need to put a 2, and a 3 here. Now, in this part, we're going to put energy on the left side because, again, it's endothermic. We're putting energy into it. So, starting off here, we have reactants. And so these reactants are at room temperature, or we'll call it in the cold state for right now. So which means they have basically 2 bars of energy, thermal energy. And they do have some chemical energy stored within them, so we'll give them 2 bars there also. Now, what happens is, if we're adding heat energy, we're going to be adding bars to our system. So the first thing we do is we heat them up. So now we have reactants that are hot reactants. And so those representing that differently now is we have the original 2 bars, plus I'm going to draw in blue here there's 2 bars of energy that's been added to the system. Our chemical energy has not changed, so we still have 2 bars there. So now, if we want to store this thermal energy that we've added into the system here, we need to change that thermal energy into chemical energy. Because if it was thermal energy, what would happen is it would just cool right back down, and these 2 bars would leave the system. That's not what happens. What we have is a chemical reaction up here on top that occurs. So these are our reactants. When they get heated up, they change into the products. And so in those products then we have a greater amount of chemical stored energy. So these blue bars are going to shift over here to the chemical state. So I'm going to draw those 2 in here first to represent that. Bottom, I still have my old 2 bars of chemical energy, so that's still there. We've increased the amount of chemical energy. Thermal energy is then left with 2 bars, and our energy flow of the system doesn't change. There's nothing that has changed in terms of that. Next one here, we have solid barium hydroxide is added to a solution of hydrochloric acid to produce aqueous barium chloride and water. The test tube feels warm. So if it feels warm, it's giving off heat, it's exothermic. So we're going to be having energy leaving the system. And again, that has to be energy in the form of thermal energy. It can't be chemical energy leaving. So let's start off here by writing the equation. Barium hydroxide is BaOH parentheses 2 plus HCl, which is hydrochloric acid. You have barium chloride plus water as our products. And then over here we have energy also. Balancing this up then, I'm going to put a 2 here and the 2 here to balance the reaction. So this is how it starts. We have some chemical energy stored on the left side here. So in terms of the number of bars, I'm going to draw a little bit more for chemical energy being stored there. And again, it's about room temperature, so there we are. So we have reactants here. Energy flow diagram. We can't lose thermal energy because it's balanced with the room. So the first thing we have to do is change from chemical into thermal energy. So when you react these 2, they interact with each other. Chemical energy decreases. So now we are left with 2 bars of chemical energy. We still had our original 2 bars of thermal energy, but we've gained 2 thermal energy bars due to the chemical reaction. Our energy flow has not changed. So these are the products here. And then we're going to do the products later. So these products, you could kind of say are the hot products here in the middle, whereas these ones are the cooled off products. And so if those are the cooled off products, we have these 2 energy bars leaving that are in the blue. That leaves us with 2 thermal energy bars, 2 chemical energy bars, and we're done. So again, it's exothermic. We have energy leaving the system right in the second energy diagram here. Next one, when a mixture of iron filing, fine powder, and sulfur powder is strongly heated to an orange glow, solid iron 2 sulfide forms. So the part that's important here is strongly heated, so this is going to be endothermic. Endothermic meaning that we're adding energy in the terms of thermal energy. So to start off with, let's write our equation. We have iron plus sulfur yields iron Fe2S3 to balance that ionic substance. And to balance the overall equation, you put a 2 here and a 3 in front of the sulfur. And over here on the left, we're going to put energy again, because we are adding energy to the system. So let's start off by putting our reactants here. So if you mix these two, iron and sulfur, they don't really do anything. It just makes a mixture. So when you put those two together, we call those reactants cold again. When they're cold in the room, they have a certain amount of chemical and thermal energy. But as soon as you add the heat to it, so as soon as we take and we add a couple bars of thermal energy here, then we're going to increase our thermal energy in the reaction. So I'm going to start by drawing those two, but then I'm going to also add in my thermal energy bars here. So now we would call these reactants in the hot stage. So if you heat these two up, they're going to begin to react. And so when they begin to react, what happens is this thermal energy changes to chemical stored energy again. So these are the products now. So as a result, the products have two additional chemical energy bars that entered the system originally through thermal energy. And we're left with 2 bars of thermal and chemical also. So the theme here is that we are adding energy into the thermal stage that can be changed into chemical, or vice versa. Again, no energy flow here because there's nothing entering or leaving the system. Here's the last one that I'm going to do. This is propane gas burns in a barbecue grill for cooking hot dogs and burgers. Assuming complete combustion, what are the products of this reaction? So propane gas is C3H8. And we get, this is mixed with air, oxygen, gas. We get CO2 gas and water. And in any type of burning reaction, combustion reaction, we're going to have energy here that is being given off. So let's balance this up before we get too far into this. 5 O2, 3 CO2, and 4 waters to balance this. So again, this is exothermic, which means that we're going to have, to kind of build on this again, we're going to have energy in the chemical changing to energy in the thermal, which then leaves the system. So let's start with our reactants here. So our reactants have a certain amount of chemical energy that's pretty high because eventually we're going to lose that chemical energy. We have a certain amount of thermal energy here. And what first has to happen is this chemical energy is going to change to thermal energy. So I'm going to draw that in blue here. That has not left the system yet. But this happens very quickly in combustion reactions. Right? That's why we see the flames. That's why things explode sometimes with combustion reactions as well. So products here in the middle, and then eventually products later on, we're going to have a cooling down effect. So that thermal energy now is going to leave the system because there is additional amounts of thermal energy. And so our products then have 2 bars thermal, 2 bars chemical. We have a net flow out of the system, which is a definition of exothermic reactions. And so that's the 5 that I have for examples for you. Hopefully these helped if you had some problems with them. And that's where we'll end this video.